So now that we've talked about concurrency and concurrent programming in terms of the concepts that are embodied, such as being able to have operations run in different orders, non-deterministic execution, the execution order doesn't necessarily match the textual ordering, talking about things like avoiding race conditions and memory inconsistencies with shared mutable state, and so on and so forth. Now let's go ahead and talk about how Java realizes concurrent programming in the Java context. And this has been around since day one, literally, of Java. So in Java, the way that you do concurrency with the object-oriented features, at least, is through something called a Java thread. And as you can see here, a Java thread is a class, or a Java thread is an object of type thread, which is a class. And the class itself contains a whole bunch of public methods and also some private methods and a bunch of fields in order to implement the threading abstraction. So some of the things that a Java thread has, it has its own stack, which is a stack of activation records to keep track of function calls so you can support recursion, for example. It has its own registers, such as a stack pointer and an instruction pointer and so on and so forth, and other types of registers for doing computations and so on. And internally, it's got some fields. You can see on the right-hand side of the screen, there's a list of a whole pile of different methods that are exposed for threads, and we'll talk about some of them. A thread can also be in one of various states. So when you create a thread, when you say new thread or new my thread or whatever, there'll be a new thread created, and it's in the new state. And then when you start the thread, it transitions it to the runnable state. When the operating system and virtual machine decide to start running your thread, this thread scheduler will pick it up and start to execute it. That transitions it into the running state. While it's running, it may do some timed operation like a sleep or a wait with a timeout or a join with a timeout, and that puts it in the timed waiting state. If the wait time elapses, it'll go back to being runnable, but won't actually run yet because it only runs when the scheduler selects it and gives it to a core to execute it. While it's running, it can also go into a waiting state by doing various calls to the notify and notify all methods. It can also block on synchronizers, such as the intrinsic lock that's part of every Java monitor object. And then also when it's done, it will return from the run hook method, which is how it runs. And that will then have the thread be terminated, and that'll make it possible for the underlying garbage collector to reclaim the memory that's associated with that particular thread. There's a whole bunch of these states. I walked through them here briefly. You don't necessarily have to be aware of all these states in great detail for this course, but you should be aware that threads are not always running. Sometimes they're blocked, sometimes they're waiting, and so on. And when they when they terminate, then they're no longer able to continue to do anything else. And so at that point, the resources that are allocated to them could be reclaimed by the underlying Java execution environment. Concurrent Java threads, in other words, if you spawn multiple threads within a given process, they can interact with each other in a couple of different ways. Now, I have particular nomenclature I use in all my slides to indicate threads running in a context. And the context in which threads run is called a process. And we'll talk more about what processes are just a little bit. A process is essentially a unit of protection and resource allocation. And within a process, there can be multiple threads. So a thread is a unit of execution. You can have multiple threads executing within a process, and a process is a unit of protection and resource allocation. Important to understand those concepts at least a little bit. And you can see here the threads that I show running in this process, which is the grayish round angle shown on the screen. They're interacting with each other by sharing state through various things like synchronizers and or message passing. So let's talk briefly about the concept of shared objects. Shared objects in this context really just mean synchronizers that can be accessed within a process in order to ensure mutual exclusion and or coordination between two or more threads. And we use these shared objects in order to synchronize concurrent operations thereby ensuring certain properties. And one of the most important properties, as we'll see in a second, which is kind of shown by this diagram, is that you want to be able to ensure mutual exclusion. And mutual exclusion is just a fancy way of saying only one thread at a time can be inside a so-called critical section accessing some shared mutable state. So that's kind of the foundation of all the synchronization concepts. So mutual exclusion is a useful property to ensure, to be careful and prevent threads from corrupting shared mutable data or shared mutable state. So I try to use images that will connote some metaphor in your mind, and I try to use them consistently to be embodying the principle of least surprise. And the principle of least surprise metaphor here is, if two automobiles try to share the same space, they will collide and corrupt the automobile state. Your car will be wrecked, or both cars will be wrecked. And so mutual exclusion is a way of keeping threads from crashing into each other's shared mutable state and therefore corrupting it. We'll talk more about mutual exclusion in my concurrent object-oriented programming course. Another key concept that's provided by shared objects is the notion of coordination, which is a family of synchronization mechanisms that ensure operations occur in the right order, at the right time, and under the right conditions. So it's really about coordination, like passing a baton. And you've got to make sure that you pass it at the right time, otherwise you drop it, or you don't win the race, or you get disqualified, or whatever. And so coordination is really more about interactions to make sure threads run at the right time or in the right order. Whereas mutual exclusion, in contrast, is about making sure that critical sections only have one thing going on at a time to make sure that shared mutable state is not corrupted. And then there's also lots and lots and lots of examples of these things. We're not going to talk about many of them in this class at all. That's the concurrent object-oriented programming class. But just a quick summary, just to be comprehensive here. Synchronized statements and methods in Java are examples of synchronizers. Reentrant locks and intrinsic locks are examples of synchronizers. Atomic operations, semaphores, condition objects, compare and swap operations that are done way down in the bowels of the Java virtual machine and the underlying hardware. Those are all examples of synchronizers. And they're very cool, but we're not going to talk a whole lot about them. There's another way in which threads interact, and we're going to spend some time on this later, but mostly, again, from the point of view of kind of a consumer of these capabilities as opposed to how they actually get built under the hood. And that concept is called message passing. And what happens with message passing is that you have producer threads, one or more of them, and consumer threads, one or more of them. And those threads can interact with each other by passing messages from one thread to the other thread or threads. Or, some set of producers can generate messages and pass them to some set of consumers. And the way this is done typically works with something called a blocking queue, usually a bounded blocking queue. And that just means that there's a limit to the number of items that can be in the queue at any one time. So you don't overflow the amount of resources on the machine by using up all the memory storing an infinite number of items in the queue. So basically the way the queuing mechanisms work is, if the queue is empty, then any consumers have to wait or block until the queue is not empty. And if the queue is full, then any producers have to block or wait until the queue is not full. And the threads coordinate their interactions that way. There are lots of Java thread-safe queues that implement message passing. So array blocking queue, linked blocking queue, priority blocking queue, synchronous queue, concurrent linked queue. Some of these things support blocking, some of these things are just thread safe, and so on. But there's a bunch of ways to pass messages back and forth. And once again, we're not going to focus a whole lot on that concept in this course. We're going to focus on other things, but just be aware that those mechanisms exist under the hood. And all the stuff we're going to talk about, like completable futures and streams, use these lower level mechanisms in order to actually implement the behaviors that we'll be focusing on in this course. So that's a quick overview of kind of classic concurrency mechanisms like threads, classic synchronization mechanisms like shared objects and message passing. Now, one thing that makes all this very complicated is the fact that there's a bunch of concurrent programming hazards you can run afoul of if you're not careful and or you're not lucky. So that's what I want to talk about now. So these shared objects and message passing mechanisms are designed to share resources safely if you use them properly and avoid various types of concurrency hazards. And as you'll see, there's a bunch of things that can get you into trouble. So probably the most common example of things that will get you into trouble is something called a race condition. And a race condition occurs when a program, a concurrent program, depends on the sequence or the timing of the threads in order for it to operate properly. And if you have that kind of a program where it only works if you get extremely lucky and all the stars align and the threads just happen to run in the right order at the right time under the right conditions, that's an example of a buggy program, because invariably, because of the non-determinism of thread execution, if you are not lucky, which is usually most of the time, unfortunately, in a modern multiprocessor and multi-core processor environment, then you'll have corruption of state and you'll end up with reads and writes conflicting and corrupting the underlying data that make up the fields in your Java programs. If you want to see an example of a race condition that's very obvious once you start running the program, take a look at this example down here below. This is something I call buggy queue, and it intentionally induces a race condition by using a queue that doesn't have any synchronization in it. And when multiple threads add elements to the queue and try to remove elements from the queue, because there's no synchronization, the internal fields of the queue get all scrambled up and the results are nonsensical and the program basically blows up and ends up with a null pointer exception very quickly. So good example to show visually and show very concretely why you have to be careful and synchronize your code properly. Another much more subtle problem, but no less problematic in practice and very pernicious, is the concept of memory inconsistencies. And these problems occur on multi-core processors, especially modern multi-core processors that have so-called weak memory semantics, where you end up with different threads running on different cores having different inconsistent views of what should be the same data. And this occurs because on modern processors, they're trying to optimize everything at the hardware level. And so as a result, you can have reads and writes in different threads that end up passing each other in memory because the processor cores are trying to cache the data aggressively to make things run faster. But the problem is, if you're sharing data between threads, you often don't want it to be cached because then you have inconsistent and out-of-date results. So this is a very serious problem, and it's very subtle. And once again, the solution is to use synchronization or other mechanisms we'll talk about. Yet another common concurrency hazard that you can run into when you start doing programming with multiple threads and multiple cores and synchronizers is the concept of deadlock or deadly embrace. And a deadlock occurs when two or more competing threads have a resource that they own, want a resource that another thread owns, and then end up waiting for the other threads to give up their resource without being willing to give up their resource. So you end up deadlocking. It's called a circular embrace, and no work gets done because everybody's waiting for someone else to give up. This example shown on the slide is a neat illustration of this. So we have thread T1, and thread T1 owns lock L1, and we have thread T2, and thread T2 owns lock L2, and T2 needs L1, and T1 needs L2, but because they already own the other thread's lock, the other thread is waiting for them to release it, and they're waiting for the other thread to release it, and they just sit there and do absolutely nothing. So that's what's often called a deadlock. And there's various ways to avoid that, but it's a very subtle and pernicious problem in concurrent programs. So mercifully, the way in which we're going to be doing programming in this course will sidestep almost everything we just talked about as concurrency hazards. So as you'll see, as we start getting into the discussion of parallel computing, the way in which Java provides parallel processing frameworks or functional parallel processing frameworks is going to eliminate most, if not all, of the need to do explicit synchronization in your code, and therefore issues like memory inconsistencies and race conditions and deadlocks will just vanish into thin air, as long as you play by the rules. And so we'll talk, of course, quite a bit about the patterns and idioms of playing by the rules when you can use these more powerful Java parallelism frameworks.